Hi, my name's Steven, and this is the first video of what will hopefully be many episodes where I talk about a variety of electronics topics, some of which will include things such as personal projects of mine, perhaps projects that I've done at the lab, to things maybe such as teardowns for items that I've gotten off of, say, eBay, or where I give you guys educational videos talking about things that I've learned in some of my senior electrical engineering courses. So actually, before we get started, I just want to apologize for the, relatively poor video recording and audio quality of this episode. Now, since this is the first recording that I've ever made, I'm just using my Canon PowerShot camera here, and it doesn't have an external mic in, nor do I have a tripod. So give me a break here, and let's get into it, shall we? So before I tell you what we're going to be talking about this first episode, I want to give you a little bit of background first. So several months ago when I was at the lab, I was working on trying to get all of these test and measurement instruments to communicate with the computer. All right. So now a lot of these instruments have this communication port on the back of them called GPIB, General Purpose Interface Bus. And the problem with it is that, computers don't have these ports natively on them. So you have to get some sort of adapter, right? So one of the most common things to be found on computers these days is USB ports. So why not use a converter from USB to GPIB, and then you can talk to your instruments. Well, that's great in theory, but there's a lot of restrictions that end up coming with that because the adapters that you can get from, say, National Instruments or Agilent, they all require you to use their proprietary drivers. Now, that's not a problem for you Windows folk out there. However, I try to use as many computers as possible running Linux, just because it offers me greater flexibility, allows me to remote into them a lot easier, wide variety of things. But the thing is that they only provide drivers for Red Hat-based Linux distributions, right? Which means at the end of the day, I can't use my preferred distribution, which is Ubuntu. So after figuring out that it doesn't work on Ubuntu, I went ahead and installed Scientific Linux, which is based off of Red Hat Linux, and then found that the Linux drivers that these companies offer do not actually have MATLAB bindings. And, for this project, we had to use MATLAB for it. We couldn't use, say, Python as our communications. So what I ended up having to do is install Windows at the end of the day. And as painful as that was for a lot of other things that we had to do, it was the only way that we could get it to actually communicate with the instruments. But this made me think, why don't I just, make my own adapter that allows me to more easily communicate between a computer and these instruments from USB to GPIB without the hassle of having to worry about these drivers and whether it's going to work on one distribution or the next, or heck, what programming languages I can even use with it. So after all this, I went out and I made, this. I made this USB to GPIB adapter. The reason that it's easier to communicate with your instruments using this as opposed to the National Instruments one or the Agilent one, as I've already mentioned, is because it uses an FTDI chip to present itself as a serial port to the computer. Now, the advantage of that is that anything that can talk to a serial port can now talk to this adapter, and thus any instrument that you have plugged into it. So what I'm going to do today is I'm just going to show you guys it communicating with my Tektronix oscilloscope, and maybe I'll show you guys it talking to an older piece of electronics. I picked up recently a Keithley 195 off of eBay with a GPIB port on the back. So I'll show you guys how it can even work with instruments prior to them more rigorously defining the GPIB protocol. So in order for me to show you how this thing works though, we're going to actually have to head away from my soldering bench here and head over to the computer so I can hook it up, show you guys the communication, show you guys some of the Python scripts that I've written to make it really easy for anybody to just use it to communicate with their instruments. All right, so why don't we go over, take a look, and I'll show you the setup. All right, so here we are beside the computer, and what we're going to do is we're going to hook up my USB to GPIB adapter to the oscilloscope there, which is a TEC 224 that actually has the measurement option in the back of it. So we're just going to flip the thing around, plug it in, and what we're going to do is we're going to measure the output from the DDS chip in another project of mine here, which is a, it's a DDS function generator. And that's going to be something else that I cover on another time. Not going to worry about that right now, but that's pretty exciting also, but not today. So we're just going to, what we're going to do is we're just going to measure the output, the direct output from the DDS, not the output from over here. That's some other stuff. But since I don't feel like turning on that power supply over there to actually power that, not going to worry about it. I'm going to measure the output from the DDS into the scope, which is what you see right now, right there. My camera doesn't focus very well. Again, I'm sorry for the poor quality, but that's what I've got. So what we're going to do is we're going to transfer that waveform into the computer over here, and we're going to do some some FFT on it and see what happens. So, as we can see right now, DDS is set to 1 kilohertz. Again, not focusing, sorry. Alright, so we're all plugged in now, and it's on a little bit of an angle, as you can see over here. But that's just because this other cable that I have is only so long. So, that'll have to do. Alright, so here we are at the computer now. See, instruments are all just right over there. We're at the computer, and it's really hard to see. I'm sorry. And I'm sure I should just use like a screen capture thing, but I'm going to be going back and forth, so oh well. So what we've got over here is we've got a Python shell, we've got the actual just quick script that I wrote, and the file browser in the background. So what we're going to do is we're going to go ahead and execute that first file, which is I just called it test.python. And if you look there, if it'll actually focus anytime this year, it says Tektronix TDS 224, blah blah blah, firmware version, blah blah blah. Which means that we just asked that for its identification. So that scope came out after the more standardized communications between instruments and computers via GPIB. So you can query it with the command *IDN question mark. Alright, so let's go ahead and now use my adapter to communicate this waveform, this 1 kilohertz signal from my DDS chip, from the oscilloscope to the computer. And we're also going to do some analysis on the data that's already in the script. What we're going to do is we're going to do the FFT of it, then we're going to properly adjust the X scale to not be from -pi to pi, but to actually represent the frequencies in question. So what we're going to do is we're going to go ahead and run this new script, so test1.py, and we're going to run it. I'm just going to import all the packages, transfer the data, and bam. So it just transferred 2,500 data points, each 2 bytes wide. So just so you guys know at home. So if we look here, it looks pretty much just that it's in the middle, and there's some little bit of stuff down at the bottom here and some other components there. But what we're going to do is we're going to first adjust the scale, because this is from 0 to like 300 kilohertz right now. So what we're going to do is we're just going to shrink that back out there, and we're going to change the X limit of our graph there from 0 to, let's say 3,000. Alright, so here we go. So what we've got is we've got this huge spike here straight at 0, because there's a DC offset, so that's where that part comes from. And then the majority of the energy here is at 1 kilohertz. And then if we look down here, there's a little bump down there at 2 kilohertz, so at the first harmonic. And then you can start to see the first one there at 3 kilohertz. So there's a data point right there, which is smaller than that one, right? So the reason that that the bins are so big here is because, well, it's only 2,500 data points. If I just did the horizontal div, we could get better resolution and whatnot, but yeah, that's fine enough for a demo. Alright, so for the next thing I'm going to show you guys that it can, well, talk to, is that it can indeed talk to these older instruments. So there's a problem with these older instruments in that it was before they decided to standardize the commands that these instruments could take back and forth, how to respond to them and whatnot. So the nice thing about the tech scope over there is that anytime you ask the instrument a question and it has to respond, your question or query ends with a question mark. So that means that in my controller, in the actual code for it, I can parse out when there's a question mark and then immediately tell the instrument to respond after it's done sending the command. But unfortunately, with these older instruments, for example, this one was made in the 80s, that functionality doesn't exist. So what I had to do is actually add another kind of like an internal system command to it that you can write. I made that command the +sign read so that it tells the controller to force the instrument that it's connected to, in this case the Keithley 195 DMM, to talk to the controller. So what we're going to do is we're going to go ahead and power this sucker on here. We'll just let it turn on. Oh yeah, nice relays and everything. Alright, so what we're going to do is we're going to run this code that I've got here. And what we've got is, all we're doing is just importing my generic instruments that I've made, defining it. It's going to be channel 16. If you saw it when it turned on, it said IE16. Default GPIB address for this instrument is 16. And what we're going to do then is we're just going to write two things to it and then, well, read from it. So the first one is going to be write YX. Alright, that's right there. So what that does is it tells the instrument, the command Y tells the instrument to not include any sort of character terminators at the end of the string. So by default, the instrument, if you read the manual, will anytime that it talks, will add a carriage return and a line feed. Not sure on the order, can't remember. Carriage return and a line feed to its command. But the thing is that my Python code, which is changeable though, but I didn't feel like changing it, uses the carriage return to signify when my controller is done actually talking to the computer. So what we gotta do is we just gotta remove that so that the carriage return is free to be used by the controller, so that the actual Python script knows when to stop. Okay, so I just put a 100K resistor in there. It's just a standard quarter watt, 5% resistor, whatever. And as you can see, it's showing up as, well, 98.8K. So, yeah, close enough. So what we're going to do is we're going to go over here and we're going to run that. We're just going to go ahead and run that script. Again, I'm sorry that you can't see the screen and I should be using screen capture for these parts, but it's easier for me to go back and forth. So we're going to go ahead and run that. And what do we get? Well, it's going to be hard to see, but it says NOHM plus then the number E plus 3. So it's saying that it's returning ohms, it's a number, it's giving us the value and the exponential, right? So as you can see here, 98.843 and then, well, times 10 to the power of 3, so E3. So that looks pretty good. And you can change, you can do everything with the front panel, just with the code, just like normal, for example, on the scope, I could change the coupling if I wanted to, or whatnot on the channels, or the divs, or what have you. But this is really convenient because now I could keep running my script if I want, and it's changed by the least significant digit there. As you can see, it's kind of floating around as temperature and whatnot. So yeah, that's pretty good. I hope you all enjoyed the first episode. I realize it's been a little rough around the edges, and watching the camera shake as I talk probably hasn't been the most enjoyable aspect of the film, but I still hope that it was worth it overall. I've got a couple of ideas planned for the next few episodes, including perhaps a teardown of that Keithley 195, overview of that function generator maybe that I'm building. Yeah, I think you guys will like that. I've also got some ideas for some educational related videos, maybe some DSP things, maybe some microwave engineering. Yeah, could be pretty cool. Anyways though, I'll see you guys next time. Later.